Assalamualaikum warahmatullahi wabarakatuh. So today we will discuss about impulse, momentum and impact. Okay, so the equation that we use in the impulse is derived from FMA. So previous chapter is FMA. So from FMA we have this one, F equal to MA, and then we derive until we get the impulse, which is this one, impulse equal to change in momentum. Okay, impulse equal to change in momentum. Okay, but so we put it here, and we have mv2 minus mv1 here. Okay, so impulse equal to change in momentum, but since we want everything to be in positive, so we'll bring this one here. So we have mv1 plus impulse equal to mv2. So actually this is the impulse. Okay, and the unit is Newton second, and this is the equation that we will use for the whole chapter, okay, to calculate the impulse. Okay, so normally if we are given area under graph, the impulse in term of area under graph, we will use this one because this is the calculation, is area under graph. But sometimes impulse also given in term of average impulse. So average impulse. Okay, sometimes the question give you in term of average impulse. In this way, where is it? Okay, this one. So sometimes we are also given in term of average impulse. So we will just replace here the term of the impulse, like we have here f dt with rt, where the r is the average impulse, time t is the time. Okay, it's different by this one. This one, the impulse, okay, which is f, this is t. So the graph for impulse might be this way or something else. Okay, so it is not a simple graph. Okay, but here rt is average. So if you are drawing the graph for the impulse, this is f or r. Okay, it's actually an average, so it is always an constant value. So that's why we just calculate directly r times the t. So actually we are also calculating the area under graph, same thing, but the difference is the r is something which is constant value. Different from here, we're using fdt because the graph might be not a constant value. Okay, that's the only difference. Okay, for example, here we have this exercise. The body in the figure moves with an initial velocity v1 given 10 meter per second, is acted upon by an impulse of 5 meter second. So actually this is a r, okay, which is average impulse, a constant value. Determine the final velocity v2. Okay, so what we'll do is we will use the equation, this one, m1 mv1 plus rt equal to mv2. Okay, and one more thing here is acted upon by an impulse of Newton second, already given 5 Newton second. It's not the r, it is actually rt. Okay, because the r is Newton, it is time the t, so it is rt, so already rt. So we put here in the equation mv1 equal to this one impulse or rt, equal to mv2. So if you put the information given, the mass is 0.3, and we have v1 is given as 10 plus this one is 5 from here, 5, okay, equal to mv2. So m is 0.3. Divided everything, you simplify, you got the v2 equal to 2.26.7 meter over second. Okay, so if you look at the answer given here, okay, this is not same, meaning that if you use this method, it is actually wrong. Okay, if you use this method, it is actually wrong. Why it is wrong? It is because you are not considering the direction. Okay, you are not considering direction. Impulse or forces and so on is a vector unit, so you have to consider the direction. In this case, we have v1 is this direction, impulse is this direction, so it's not on the same direction. So you have to resolve all the component into x and y. Is the simplest direction that we can use in terms of x and y, so that once it is in the same direction, then we can calculate. Okay, so for example here I've resolved into two direction, which is x and y. So first I'm taking all in x direction, so mv1x plus impulse in x direction equal to mv2x. Of course, m, there is no direction for m is the mass, so the ones that have direction is the impulse and also velocity. So v1 here, you see v1 here is in y direction, so vx equal to 0, 5, so because given here 5, 0.3 v2x is the one that we want to calculate. So from here we have the v2x, put it here in the same equation, and v1y, because we have y here. Okay, so full. Then impulse is 0 because we have only in x direction, so here is 0. It's equal to 0.3 v2y. This is the one that we want to calculate, v2y. So from here we have v2y. You combine these two. Okay, this is v2x, this is v2y, and then you combine, you get the v2, okay, which is the square root of, equal to square root of v2x squared plus v2y squared. Okay, and then you get the answer here, and then the theta is tangent minus 1 v2y divided by v2x. Okay, so you got the theta equal to, this is v2. Okay, so you combine that two, you will have the v2 and also the direction. Okay, again use the equation mv1 plus f dt, okay, equal to mv2, but you have to consider the direction. Okay, you have to consider the direction because it is a vector unit. This example, if the value of impulse is given, but sometimes or most of the case in our syllabus, you will be given in term of graph, okay, which is this one. Okay, for example here, the impulse given in term of graph, which is here, instead of given directly the value, you are given graph. So this is f, this is t, so you get f dt, you will have the impulse. Okay, so equation m, this is f dt, f dt, okay, equal to mv. So the equation here to replace fvt depend on the type of graph. Okay, here we have a triangle, so half f times t, because it is a triangle. Okay, so if the question said, let's say here in this case we have mu equal to 0, okay, the first case mu is equal to 0, here I have mu equal to 0, meaning that it is a frictionless surface. There will be no friction that counter the movement, so we have the component acting by impulse by force F. Okay, so the F will pushing this component to this direction, and the force given F is following this graph. So if the question asks you to find the something at t equal to 1 second, 2 second, or 3 seconds, so the part in the middle here, of course here the m2 you can replace, but the thing in the middle here you have to replace by, let's say you want to at time equal to 1 second, so your graph will be only here. This is only your graph. Okay, this is actually a trapezium. So the trapezium, the area under graph equal to half f1 plus f2, the these two side, okay, plus these two side, you get the area under graph, you get the this one, and then you times the t, which is up to 1, so you have 1 here. When the question asks you up to 2 seconds, so you put here until 2 seconds, you have the complete triangle here until there. So only half times F2 times the time is 2. But if the question wants you to find something at t equal to 3 seconds, what we'll use is you will put half F2 times also 2, because even though the second is here, it's only 3 seconds, but the forces given is only up to 2 seconds. Okay, so you can calculate only for this part. This is actually to replace this one. For this part, okay, it is only up to 2 seconds, because you have the graph up to 2 seconds. Even though the question will ask you at time 3 seconds, 4 or 5 seconds, here you can only replace only up to 2 seconds, because this is the only time available. The force available to you is only up to 2 seconds. In this case, it is if the friction is 0. But if we have the friction here, we will have one friction force that oppose the direction of the motion. So the force will push the component here, so the component will move to this direction, but there will be friction that oppose the component. Okay, so the equation here, instead of just area under graph for the F here, we will have to minus the friction. So this is the friction. Okay, so the equation for friction is F equal to mu, in this case the friction of the moving component, so mu kinetic times N. So the friction, as long as the component is moving, there will be the friction. So the friction, the value of the friction, kinetic, it will be constant. So that's why we have a constant value of friction here equal to mu N, and the T is the time. As long as the component is moving, there will be a friction. So instead of here, I'm showing you before, we have at 1 second. So we have this thing, trapezium. So we have half F1 plus F2 time 1 second. But we have to minus friction. This friction, so minus the friction here. In this case, we have friction, which is mu N, and the time is 1 second. Okay, if we go to 2 seconds, here we have up to 2 seconds. So half time F time 2 minus mu N, and the time is 2 seconds. Okay, and the last one for time 3 seconds, we have seen before that even though it won't calculation up to 3 seconds, because the force given is up to only 2 seconds, so you can put here only 2 seconds. But for the friction, because we know that as long as the component is moving, there is a friction, here will be times 3. Okay, as long as the component here is moving, there will be friction. So here will be 3, even though here we only 2 seconds, because we have different graph from here and here. It is the T here is as long as the component is moving, there will be friction. That's why I'm putting the T equal to 3 here. But here we only have T up to 2 seconds. Okay, so this if there is a friction. So looking at this example, we have a force P varies with time as shown in the graph. Okay, so we have a component here 10 kilo pushing by a force P here, which is not a constant force but varied using this graph. Okay, it is not a constant force but varied using this graph. It starts by 100 Newton but going slowly, going downward up to 40 Newton, and the force given only up to 2 seconds. Okay, if the coefficient of kinetic friction between the block and the surface is 0.4, so you are given the mu equal to 0.4. Determine, so the information is here, m equal to 10, v, determine the velocity of the block at t equal to 3 seconds. Okay, determine also the time ts when the block is stop moving. Okay, initially at rest. So here, initially at rest, I'm taking the v1 equal to 0, initially at rest. Friction kinetic is given 0.4. So the first one is, what is the v2 at t equal to 3 seconds? And the second one, what is the ts? I'm putting ts here, the t stop meaning that T at V stop. What happened here is when the this component is pushing by the force P, a big P, so the component will start moving. But after 2 seconds, there will be no forces. There will be no forces. If there is no friction, this component will continue moving, will not stop. But because of the friction, at one time the component will stop moving because of there is friction opposed. So there will be force here and there will be friction opposite direction. Okay, that's why the component will stop moving. Okay, so we apply this equation, mv1 equal to f dt equal plus f dt equal to mv2, and the f dt, the impulse, must include the area under graph for the forces given minus area under graph for the friction. Okay, so here is area under graph for the component and here is area under graph for the friction. Okay, this value you have to calculate, mu n. How to calculate the n? N is, we have this figure, this is mg, okay, this is n, so n equal to mg. Okay, it is a normal force. So here mu n, of course you have mu is given 0.4, so 0.4 times mg times you have the n. Okay, so here is 0.4, m is given as 10, g 9.81. Okay, if nothing stated, you will use as 9.81. Okay, so replace this equation with the information that you know, m times 0 because start from rest, plus, okay, so this is for the forces. So the force at 3 seconds. So at 3 seconds, here is at 3 seconds, but the force is only given up to 2 seconds. So you can only calculate the force here. You cannot do nothing because there's nothing here. So you only can calculate the force up to 2 seconds. So half times the length of these two sides, 400 plus 100, 40 plus 100 times 2, because the time is 2 seconds. So you get the area. So actually this is area under graph, this one, area under graph, minus the area under graph of friction. So you have to calculate area under graph for this one. So 0.4 like this one I'm putting here, times 3. Here the time is 3, even though here is 2 because the time, the forces only given up to 2 seconds. But as long as the component is still moving, there will be friction. So the time, the time here for friction is 3, same as the time that is required, asking from the question. So putting here, you will see that at the end you have the this equation and you get the v2. Oh, tak nampak. So you get the, from here you only have one unknown, so v2, you can solve this one, you got the v2. Okay, so the first one, v2 at t equal to 3 seconds. But second one is, what is the v2? The question asks you what is the time when the component stop moving. Okay, the t when the component start moving. So we use the same equation here. Okay, but the difference is start from rest, so here is 0. Stop moving, this part is also 0. Okay, so we have the graph for the this is a graph for the forces, same graph. So it will only move up to here, 2 seconds given, but the friction is going straight until it stop moving. So this is t stop. Okay, so the friction will be up to mu n until it stop moving. So this one is 0, 0, this one is 0. We only have this is calculate for here. So half times 40 plus 100 times still 2 here because it is only given up to 2. And then 0.4, this is mu, this is n, which is m times g times t. T is the one that we want to calculate. So here is area under graph for the force, here is area under graph for the friction. Okay, so what we call it as impulse. So simplify this one, you have the t, and then calculate, you get the t is equal to E equal to 3.57 seconds. This one. Okay, so that's it for the impulse. So if the question asks you to find the impulse, actually this is the impulse. If there is a friction, you put friction minus friction. If there is no friction, you just calculate using this area under graph. Okay, so that case, the first case and the second case, this is the second case, which is we put the force, a big value of force, and then the component will start moving. Okay, we consider component directly start moving, and then we calculate what is the velocity and so on. Is considered as a simple question, because later on here we will have something different. Okay, previous question I'm giving you the ft is like this one. Okay, which is we start here at the big value up to smaller one. Okay, and the consideration is once we put a big value, this component will directly moving. Different from this one, we here we have the graph where the f start from 0 to some value. Okay, so from here we still not know at which time, which t, the component start moving. So we have to calculate where the component start moving. So because the impulse here can only be calculated using the graph of component start moving, not when the component is still static. Okay, so we need to know at what time t the component start moving. Okay, this one directly we can consider the component moving because it have a big value. Here we have start from 0, of course. Once we increase the force, and because of there is a friction, there are friction that oppose the direction. Okay, friction, we have friction static and friction kinetic. Before moving, it is a friction static. Okay, so we have to calculate at what point the component moving. So how to calculate the component is moving? So we can calculate that if we have this force is actually bigger than force of friction, so mu static times n. So if the force is bigger than mu static times n, the component will move. So as we know, we have here the graph for the friction, which is like this one normally. Okay, here is a maximum point, which is mu static. Okay, mu static. Okay, so once it depass go more than this value, it will start moving, which is at this point it will start moving, and we will use the mu kinetic. So that's why normally there will be two mu static and mu kinetic. So how we know which is it will start moving once we have the f is bigger than mu sn. So even though the graph given to us here, so once we know the t, that when the component start moving, the graph that we will use in the calculation is start from t moving. So start from here up to here. So only this graph we can use. We cannot use the whole graph like the one is given. Okay. So the challenge here is to calculate and to know at what point at what time the component start moving. Okay. So even though the graph given is from 0, the one that we will use is from the t1, which is t when it start moving up to the t given, and the friction also we start from moving up to it stop moving. Okay, as long as it is moving, there will be friction. Okay, so the question is, I have this one. Block A of mass 2 kilo, so we have 2 kilo here. 2 kilo. Initially at rest, so V1 equal to 0. Is acted upon by force P, which abide by the relationship PT as shown. So we have force P here using this graph. If the coefficient of static and kinetic given, so mu s is 0.4, mu k is 0.3, is normal. Normally mu s is slightly bigger than mu kinetic. Okay, so determine velocity of block A t equal to 3 seconds. Okay, so we cannot calculate directly. We have to first find at what time the component start moving. So say here, check when the component start moving, which is when this given p is bigger than mu static times n. So mu static n equal to 0.4. This is given. 2 is the mass of the component, n is g. So we know that n equal to mg. So just replace here. Then you got this value mu static times n. Okay, so this is the value of mu static n. Okay, so so mu static n, and we know this value, but we want to know what is the time. So you have to use the this figure. Okay, we have this one. Okay, this value here is, so I'm using actually this value. Okay, so here is 10, here is 2, so I have 10 is 2. Okay, so I know that we will start moving at here, which is the value of 7.848 Newton. So I have to do, you can do either you take the slope of the graph here, because we have the same slope, or anything. So like here I'm using 10 divided by 2, so 10 divided by 2 equal to 7 divided by this length. So this length divided by x, y divided by x, so we have actually the slope of the graph. So since the slope is same, so even though I take in here divided by this one, I will have the same slope. So this one will be equal to this one. So simplify that, you will have the t1 1.569 seconds. So it will start moving from 1.569 seconds. So your calculation will only start after that one. So we have this. Okay, so the friction T here is of course same as that one. So mu k times n. So we have this is the friction. This is for friction. Okay, this is for friction. So our equation mv1 times plus impulse equal to mv2. So the impulse here we have 2, which is one from here and the other one is from friction. Okay, so v1 is start from 0, so this one is 0. v2 is what we want to calculate. So we have this one f dt, because we have we will use this one, start moving until the end of the graph, because the calculation wants you up to what, up to 3 seconds, right? So up to 3 seconds, which is our graph is here, start moving here and go to up to 3 seconds. So this is the area under graph. So that's why I'm using the first one here, half time here. So the first one I'm using this part. Okay, 10 plus 7.848. Okay, this one plus this one times the length. Length here is 2 minus 1.569. So we have this triangle first. So here is also only for this triangle. Okay, and then I have to plus here. Sorry, I have to do plus this thing. Okay, plus this thing. This one is actually to take this area. So plus 10 times 3 minus 2. So by doing that, I have this one. Okay, so I have to put the minus for the friction. So friction, this value is calculated here, so I'm putting there, and the time is 3 minus here is, okay, sorry, here is 1.569. Okay, the time when it start moving equal to v2. Okay, so v2 will be equal to simplify this equation, you will have the v2 equal to 2.71 meter over second. When the t is 3 seconds, you have the value of v2. So same, if you want to calculate this one, time when the block stop moving, you will use same method by this one. Only the difference is you just replace the V2 by 0, so like this one. Okay, so I have this two part. I'm replacing the V2 equal to 0, V1 is equal to 0, so I have the 2 0 here. So leaving us this first part is for this one. Okay, so one go here, the other one is here. Okay, but even though the time is more than 3, but here we can only replace by up to 3 minus 2. Okay, which is suitable for the graph. We only have up to 3 seconds, but the friction will go on up until the component stop moving. So that's why the T here is the T1, which is until the component stop moving. So here is the time. We are taking time from here to there. Okay, so we have this one. Simplify the equation. You have T1 equal to 3.92 second when the component stop moving because of the friction. Because the force only given up to 3 seconds. After 3 seconds, the component will continue to move, and because of the friction, it will going slowly and slower. At the end, the component will stop moving. If there's no friction, the component will continue moving. So okay, so that's all for the impulse momentum. Remember, we use only this equation, mv1 equal to impulse plus impulse equal to mv2, but the impulse itself is depend on the graph. Okay, in the graph, if there is a friction, you put the friction. If the impulse force start from value which is small, from 0, you have to identify at which time the component start moving, and our calculation will based on time where it start moving to the time where the question asks you to calculate. Okay, so that's all for now. Thank you. Assalamualaikum warahmatullahi taala wabarakatuh.